So we want to talk about the variance of sums of random variables, and especially we're concerned with when the variance of the sum of two random variables is equal to the sum of the variances. Right? This is not always true. So note that just by definition of variance and covariance, the variance of x is equal to covariance of x and x. So we're going to apply this definition to variance of x1 plus x2, right? So that's just the definition that we used over here. And we're going to use the linearity properties of covariance. So we can break this covariance down into, so first over x1 and then over x2, like so. So two covariance terms. And then we can break these into two different sums, right? So we have covariance of x and x, x1 and x1, and then x1 and x2, right? Then we have covariance of x2 and x1, and then x2 and x2, right? Now note that this is just variance of x1, right? And then covariance of x1 and x2 is the same thing as covariance of x2 and x1 by the symmetry property of covariance, right? So we have these two sum to two covariance of x1 and x2, and this is just variance of x2 by definition. So for this statement to hold, we actually just need that 2 times covariance of x1 and x2 is equal to 0, or just covariance of x1 and x2 is equal to 0. So remember that this just implies that uncorrelated, that x1 and x2 are uncorrelated. All right, so note that independence of x1 and x2 also implies that covariance of x1 and x2 is equal to 0. So if we have two independent random variables x1 and x2, then variance of x1 plus x2 is equal to variance of x1 plus variance of x2. So this is actually kind of neat. So we'll see that now. You can check for yourself if you have any random variables x1 through xn, then the variance of x of the sum, right? So x1 plus x2 plus dot 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 plus xn, so that's what this is equal to the covariance of xi xj from I and j equals 1 to n. Now you can using the covariance identities, you can show that we have this variance of xi terms, and then we have covariance of, these are called cross covariance terms. And since we have symmetry of covariance, so covariance of xi xj is the same thing as xj xi, right? So this term over here becomes 2 times all the indices that I is less than j of covariance of xi xj, right? So you can check this for yourself. This is a pretty good exercise. And then from this statement over here, you can clearly see that if we have, so when we say independent, we mean mutually independent. So, but you don't actually need mutual independence. You just need pairwise uncorrelatedness, as you can see from here. But if you have independent random variables x1 through xn, then you clearly have that the covariance terms are 0. The cross covariance terms are 0. So variance of the sum is equal to sum of the variance. Now this is pretty neat because we can apply this to our example over here. So we want to find the variance of the binomial random variable. And if you try to use the definition of variance, this is going to be very, very computationally heavy. And we don't want to do that. So you can recall that if x is a binomial random variable with n trials, and then p as a success probability, then that binomial random variable x is the sum of n Bernoulli p random variables. So the Bernoulli random variables are, the 1 or the 0 random variables. And these xi's are IID, right? So it's the sum of n IID Bernoulli p random variables. And our claim is that variance of x is equal to n times p times 1 minus p. Now the proof is very simple. Variance of x is equal to variance of x1 plus all the way up to xn. This is by definition of the binomial and the Bernoulli random variables, independent Bernoulli random variables. So we applied this. Now, since they're independent, so remember from the corollary, since the xi's are independent, we have that this implies that the variance of the sum of random variables is the sum of the variances. And it's straightforward to calculate that the variance of the Bernoulli random variable, xi, is equal to p times 1 minus p. And then that's the same for all of them, since they're IID. So we have just n times p times 1 minus p. That's it.